Hi
Hello,
there.
Paul.
How are you?
Hi. Good. I don't know who's talking. Oh, Alfredo, is that you? Okay.
Yes.
Hello,
I am Alfred
Alfred. Okay. Sorry.
because I was born in the United States. I was born in New York.
Oh, no, we're good.
That's because my name is Alfred, but really I'm Venezuelan, more than American.
Oh, okay. That's good to
However, I
know.
was born in New York.
Oh,
That's intimidating. I'm going to change my background.
Yeah.
oh, boy. Yeah.
How
I'll
are
change mine. Yeah.
Are you at home, Dale?
Yeah. This is, yep. We're supposed to get some thunderstorms here in a little while. Right now, it looks all right. So,
So, Alfredo, the Zoom was telling me that the meeting was on the
the
25th.
25th.
Yes, I already arranged that. There was a problem because we changed the dates several times, but it's already
So whoever gets into this link will land here.
exactly.
Okay.
Felix,
I got here. So, and I saw that earlier, but then I don't know.
I invited Janelle Larson.
Okay. I think Marietta is coming and one of my students is coming.
Yeah, I sent Marietta the link.
Okay.
So let's hope.
Félix,
But
ya
I-
estás de coanfitrión, ¿oíste?
Sí, ya lo vi. Ya lo vi.
Hola, Félix.
Hola, ¿cómo estás? Hi, how are you, Dale?
Oh, hi, Felix. Good. Nice to meet you.
My friend, he's a medical doctor. He's doing telemedicine with the local Indians in Venezuela. And he's very interested in listening to your conference because they have a lot of problems generating electricity because, the fuel is very difficult to obtain. And this kind of electricity that you are able to generate creates a new opportunity for the telemedicine in Venezuela, particularly in those areas where no electricity is available. They have to generate it locally with the fuel plants, the diesel plants, those kind of.
Okay. Yeah. Well, this just makes a little bit of energy what we're doing here. But I've seen some other, there's a lot of other things, using if there's any available water source, just a small stream, you can generate a surprisingly amount of energy to power internet enabled things. So that's photovoltaics are always a nice fallback too, but yeah.
How much energy are you able to generate at home? For instance, opening and closing doors and all those kind of.
Well, we're looking on the order like a door opening. It's about 3 or 4 joules of raw energy. We can't then the process of storing that somehow so that we can use it later, getting it on the batteries or getting into, we use in our work here, we did just charge some supercapacitors just to test the idea. But we were able, it's on the order of 3 or 4 joules per door opening, which was more than we needed for our application. So that was the upside of that. We can burden the user. You can put more, the person has to push the door harder. We've been trying not to burden the user much at all. Here we had about a 13% burden to what it just would take to open the door. But the student that's working with me has done some measurements on some doors on campus and found that just doors that have, that can also be opened automatically for handicapped folks, those doors require a lot more energy than we are using in our application here. So people are used to opening doors that are present a lot of resistance. So if you can burden your user a little more, you can store a little more energy. So it's a trade-off. You know, people are used to doors opening fairly easy, but if you get used to it, it could be a new way. I don't know. I look at revolving doors. Yeah.
You can also use those kind of, you know, old machines to.
That's old school magnetos. Yeah, sure.
Mhm.
I have some flashlights like that.
You need some slave doing the.
Oh. Well, that's a whole other topic. So. Yep.
Well, Janelle is in.
I saw Janelle's there. We got some other folks coming in there. I hope there wasn't a problem with that link and that date.
Well, my son is going to be in the talk. You know, Francisco, do you remember him?
There he is.
Oh,
yeah,
there he
he's
is.
there. Okay. So, yeah. Oh, there's Marietta. Okay.
Marietta.
Janelle's eating dinner. All right.
She's hiding. She doesn't want you to ask for a salary raise. For doing international service work.
Well, it's going to be a big section in my faculty activity report for this year. So,
hi, Marietta.
Hi, Paul. How are you?
Good. Good to see you. Wow.
You too. How things been?
Good.
Good.
Good. It's been great.
Very good. I couldn't miss hearing Dale speak. I couldn't miss a chance.
Right.
Did you get my invitation or?
Well, Dale sent me one. I did see yours earlier. Yeah.
Okay. So the link I sent you did work. Okay.
Yeah.
I sent it to a student, and I'm not sure if he's going to be here. He missed an earlier meeting at 5 o'clock with me, so I don't know.
Okay.
Would Francisco count as a student?
Sure.
My son?
I've had him in class when I filled in for Henry Ansell when he was out ill. I think Francisco was in my class.
Yeah.
Yeah.
Correct.
EE210. Yep.
EE210.
Yep.
Oh, I think he.
No, I don't think so. I can check the grades. I'm pretty sure I finished the semester. I think. No, I didn't finish that semester.
Francisco.
Henry gave the grades.
Hey, how are you guys?
Hello, Francisco. Good.
Hey, Francisco, Dale remembers you from the EE210 class.
Yeah, he was listening, I think.
Yeah, I was listening. Yeah, I was honored. Yeah. It might have, I don't know if it was E210. It might have been like it might have been like a later course, but yeah, I definitely, I remember having you, and I remember you filling in for Henry and stuff.
Yep. Yep.
So, shall we wait?
How many folks do we expect?
Let's wait some more minutes to be sure that.
Yeah. Okay. It just got quiet here. I'm just watching the radar for thunderstorms.
The weather.
No,
Yep.
Not a fan of thunderstorms.
Is it coming? Is there one coming?
It said.
I still get the text messages from Berks.
Oh, yeah, you got to get out of that.
But if I get an alarm at Berks, it'll hit Wayne like an hour or so later.
Yeah, so it gives you a heads up.
Yeah.
Yep. It's a pretty broad area that it gives the alerts for. I don't know what the coverage area is, but it's not just Berks County. It's a pretty, because last week,
it's a wide area. But you, I mean, I've timed it. Whenever I get an alert from Berks, it'll hit us like an hour or so later.
Okay. Well, just as long as the internet stays on here, we'll be good.
We'll be fine. I mean, sometimes the connection with Venezuela gets a little erratic, but it has never happened in our meetings.
Okay. No, it looks good now.
Yeah, it's usually, if you go outside the capital region, outside Caracas, you might get, you know, an erratic signal.
Comes someone else.
Yes, Marta.
Marta, right. Marta.
Buenas tardes. Hello, how are you?
Okay, ¿cómo está?
Hola, Jorge.
I was just waiting to be silent around to open my micro. I at home, and then there are some other people talking.
We're watching you.
Yeah, nice to meet you. I am very interested in your presentation. I am from the soft area. I am from the computing area.
Okay.
No, not from, but I read you work on that. You have also a lot of experience in that area. Okay.
Yeah, I do some microcode, microcode programming. Yeah, so that's
microcode. That's interesting. Now I am teaching the first course in computing for engineers at Simon Bolivar University.
Oh, all right.
Yes, and then what happened is that everybody is interested in the high-level language, and they use Python. But I insist on not only on working on C, but on assembler. So I was talking to them about the importance of microcode. So it's interesting that you mentioned that.
Yeah, if you want to do something fast, you still have to do it in
Exactly.
assembly.
Exactly.
And you want to be able to control the rate.
Yeah.
You don't want to rely on the compiler to do it for you. So yeah, it's still how it's done. It's still everybody use, if you have a fast routine you need to run, you want to run an assembly.
Yeah, but I am working, yes, I am working also in the philosophy of computing. So I am interested in relate what is the quantum computing, which is the most advanced area, which the computing done by the prehistoric people. That they use the sun to compute and the moon.
To compute lots of things.
The time
to plant. Right.
To compute the time, that was the most essential thing, to compute the time.
Sure. When to go to bed, when to get up, when to plant. Sure.
Exactly. Yeah. And of course, since then, it's important computing to the well-being of society.
Sure.
It's not just with the computers, with the old ones also.
Well, there's just some really interesting documentaries about the GPS system and dating back to when they were trying to find longitude on ships out at sea. And it came down to measuring time. And that's what it still is with GPS. And the saying is that to know where you are, you have to know what time it is, because you're measuring small distances, in time to determine position. So just like they did on ships in the 1600s, late 1600s, early 1700s. Yeah.
Dave, tell me something. Are you going to use some computer aids or?
Yeah, I have some PowerPoint slides.
Okay.
I'll share the screen when we're ready to start. I'll just.
Yes. Now you are permitted to share the material.
Okay.
You have.
All right.
You're a co-host.
All right. Were we ready to start? Yes.
we're ready to
Okay,
start.
I'm ready.
In this opportunity, Félix, entonces si quiere empezamos a grabar.
I'm sorry, are we waiting for other people or?
Yes, we're
we're going to start.
Tienes
Okay,
que quitar tu grabación.
all right.
We're going
Me han diseñado para estar en espera hasta que me activen, como cuando dices, hey Google. El indicador de estado del dispositivo te indica si me han activado. Mientras esté en espera, no enviaré lo que
Some
digas
Zoom
ni a
tools got to move here. There we go.
Yeah. Okay.
We got a very Hispanic accent.
Wow.
Well,
Today we're going to present Dale Lead Wheeler. He's going with the conference, a door motion energy harvesting system for powering an electronic door lock. Mr. Paul Esqueda is going to be our co-amphitryon, and he will handle all the conference question and answers in between. No? However, first presentation, I'm going to introduce Dale. Dale is a PhD doctor. I'm going to make a translation of the matters. I'm going to listen from Dale in Spanish, and then Paul is going to do that in English, and you will start the conference, okay?
Okay.
Vamos a hablar hoy sobre la recolección de energía generada por los humanos. La recolección de energía de fuentes pequeñas y no convencionales se está volviendo más práctica a medida que surgen medios de almacenamiento de energía de mayor densidad y se puede integrar electrónica inteligente de potencia ultra baja en el sistema. El acto de un ser humano abriendo una puerta puede emplearse como un medio para generar electricidad que puede ser capturada y almacenada para su uso por dispositivos electrónicos. En la aplicación que se presenta, la energía requerida para operar una cerradura de puerta electrónica de deslizamiento de tarjeta se obtiene del movimiento de la propia puerta. Se utiliza un pequeño generador electromecánico montado en bisagra para convertir el movimiento de rotación de la puerta en energía eléctrica. El voltaje de salida del generador se incrementa al requerido por el sistema de bloqueo de puerta con un convertidor DC-DC personalizado. La energía de salida eléctrica del convertidor CC-DC se almacena en un superconductor para su uso por la cerradura. La energía neta recolectada es mayor que la requerida por la cerradura para realizar el procedimiento de desbloqueo, por lo que el sistema es sostenible. En esta presentación se presenta la configuración de prueba y los datos obtenidos de varios escenarios de apertura de puertas. Se presenta y discute el diseño eléctrico y mecánico del sistema de recolección de energía. Se describirán los problemas y limitaciones del sistema de recolección de energía propuesto. También se presentarán los trabajos que se están llevando en curso y los futuros que se piensan realizar, incluidos los métodos alternativos del almacenamiento de energía. Bueno, el profesor Dale es PhD, graduado en Ingeniería Eléctrica en Lake University, Bethlehem, Pensilvania, en el año 2000. Su primer título también fue Ingeniería Eléctrica en la Universidad también de Penn State, en University Park de Pensilvania, en el año 84. E hizo una maestría en Ingeniería Eléctrica en Syracuse University, en Nueva York, en 1989. Es profesor asociado de Ingeniería en la Universidad de Pensilvania. Tiene más de 30 años de experiencia combinada en diseño, análisis y prueba de circuitos electrónicos, más de 25 años de experiencia en desarrollo de software utilizando LabVIEW y C integrado, lenguaje C integrado, más de 25 años de experiencia en desarrollo de software utilizando LabVIEW y C integrado, y más de 19 años de experiencia en desarrollo y la impartición de cursos de ingeniería a nivel universitario. Tiene un certificado de ejercicio profesional como ingeniero eléctrico obtenido en Pensilvania. Actualmente está inactivo ese certificado. Esos son certificados que exige, vamos a decir, el Colegio de Ingenieros de cada estado allá. Un certificado de competencia profesional. Antes de comenzar su carrera académica, trabajó en IBM Federal System y en Lockheed Martin Commercial Space System como ingeniero de diseño de hardware y de software. Es experto en varias herramientas basadas en informática para simulación de circuitos, cálculo científico y manipulación de datos, capturas de diagramas esquemáticos, dibujo mecánico, control de instrumentos y adquisición de datos. Y domina estos lenguajes LabVIEW, MATCAD, MATLAB, PSpice, Multisystem y C más embebido. Bueno, welcome, Dale. We are very interested in the topic you are going to explain to us today because we need energy in many places in Venezuela, particularly in our homes. Sometimes we don't have enough to start with our computer or,
Oh boy.
Or to have energy for our mobile equipment, for our cellular, no? Okay, you can use all time you need, and then we're going to have a conversatorio, no? The opportunity to ask you some questions,
Sure.
you will answer, etc. You are very welcome.
Okay. Well, thank you very much for that introduction. It sounded better in Spanish than it does in English, I think. It was really good. Yeah, it's a pleasure to be here. When Paul asked me to do this, I thought this was a really interesting opportunity. So thank you for inviting me. So yeah, this work that we did a few years ago with my colleague, who I'm showing on the screen here, Thomas Gavigan. He has since retired. He was my mechanical engineer. I'm an electrical engineer, so he was my mechanical engineering counterpart, helping on this. And when we did the first work on this, we were looking at harvesting energy from humans opening doors, and we didn't really have a specific application to use the energy. At the time, we were in an older building on campus, and all of the doors for offices just had a metal key lock. We didn't have any electronic locks on them. So we were doing this ahead of time, looking at methods for saving energy, or excuse me, harvesting energy, and perhaps using it to power maybe exit lights or things like that in the hallway. But then we went to our new building, and all of the locks on all the doors had a card reader, and and they were battery operated. And all of a sudden, we had a captive application right there on the door that perhaps we could use this energy to power. And what even helped motivate us a little more was that we found they were having a lot of battery failure issue. I mean, run down batteries. It used a lot more power than they thought. We were replacing batteries on really short intervals. So, it kind of motivated us into this particular work with a specific application. So that was, so what we had done before, we were looking at not necessarily office doors, which was the later work now is specifically small office doors. But we were looking at more stairwell doors that were opened by hundreds of people a day. That was our original work. And we, in our previous work, we had designed and installed units onto the hinges to make measurements of how far the doors opened. It recorded, the times of day, how, actual swing of the doors. And then we characterized those doors and knew how much energy it took to open them. And putting all of that together with the data we collected, we could come up with numbers for the amount of energy that humans were using to open these doors every day. And that was hundreds and hundreds of joules of energy. But now specifically here, we're looking at probably one person is opening this door. It's an office door, so it's typically the person that uses the office. And the number of times they might open it in a day. What we were trying to do was see, could we harvest enough energy on each door opening to replenish the energy needed by the mechanism of the lock to unlock the door each time? Otherwise, if we didn't get there, it was diminishing returns. We needed to be able to at least break even. And we found, spoiler, we found that, yes, we could capture more energy than we needed on each door opening. And as we were talking a little bit before we got started here, not everyone was there yet. We were concerned about not burdening the user. We can always impose heavier loads on the door opening. Some of you may have experienced this with even just simple screen doors or storm doors that have a heavy hydraulic closer on them or a spring. Humans get used to a certain amount of resistance when they're opening the door. So what we were looking at here was not imposing a large burden on the user. So that was kind of our parameters for our study. And as I mentioned, we had some issues with batteries. We still do. We still have that issue because we have not implemented this. We're academics, so we haven't gone to the step of approaching the manufacturer and implementing this. We studied it. Some other things we did, we wanted to make it easy to install. We didn't want to have to drill holes in the door. We didn't want to have to modify the hinges. We wanted it to be able to be removed and not leave a lot of damage on the door. As it mentions here, we wanted to be able to open, some of the doors open to the left, some open to the right. So we wanted, we were looking at many practical things here right at the beginning. Just so we consider those as we went down this path. So there's some photos of what it looks like. So from the hallway side, I don't use a lot of Zoom this semester. So they're not outside. So they're in a controlled environment. But the top is, as we can see with the cover removed, these locks are actually web enabled. So they're actually on our campus now, downloading information to them as to whose card will open the locks. It's supposed to indicate health of the lock back to the main system. So the top has a plastic cover. So we can see that here is the battery pack, and inside, it's got 6 of a standard AA size primary cells. They're not rechargeable, all together in a pack to create 9 volts that used by all the electronics and the mechanism to, it is a lock. So it has electromechanical parts to it. It has to release the lock. So everything's contained behind that cover on the inside. There is a deadbolt throw here, but that's not part of the mechanism. We're not, that's all manual. We're not looking at that. Okay, so this is actually me. This is my office. We did some sort of low-tech measurement, maybe high-tech mix of old school and new school, but we can see on the floor here, we put masking tape on the floor and we marked it every 15 degrees of motion. So we got a total of about 60 degrees here. And we typically, for a person, we went down the hall and looked at people opening doors, and typically when a person enters their office, they don't swing it back all the way 90 degrees. Some folks have got furniture in the way they can't open it all the way. So we're looking at about 60 degrees was typically the opening for a person would open the door to enter the office. So we made several videos, and just looked at the timing. We could go look at it frame by frame to determine speed, angular speed on this. So rather than having instruments on our hinges in order to make these measurements, we kind of went with a video method of doing it. And we did several trials and different people did it. And typically we got on the order of about a 7.5 RPM speed of opening the door for the 60 degree opening. So that set up our parameters for the type of motion that we would have, that we could work with to power or to produce the energy. And so that was our baseline, about 7.5 RPM for 60 degrees. And yes, it was, you were starting up, it was about 7.5. So just using that knowledge, and then now this is some real mechanical stuff that wasn't my area. This was Tom Gavigan's area. But we wanted to look at, even if, you know, rather than putting other instruments on the door, if a human, these are large wooden doors. So they're you know, they're roughly 36 inches. So it says 914 millimeters wide, weigh about 45 kilograms. So when this gets swinging, it's got a good bit of momentum, and it got that momentum from the person opening it. So this was kind of an indirect method of determining the energy that a human is used to putting into the door to open it. It's just what they expect. It's custom. So, you know, based on the parameters of the door, the size, the mass of it, come up with the moment of inertia, and we could determine the kinetic energy that would be in this door as it was moving at 7.5 RPM. So that told us that's about the amount of energy that a human typically puts into a door that size just to open it. So that gave us we had no idea what the feel for the numbers were. You know, was it 100 joules? Was it 0.1 joule? We had no idea. You know, so this was a good, helped us to visualize, you know, the type of energy that a person is accustomed to in opening a door. All right, so then we started looking on the load side, the using side, the energy using side. And here we took data, that lock that I showed you that we had opened up, that was actually in my office. And we put some instruments on there to measure current. And we looked at what happened in the sequence of unlocking the door. So what it's showing here is that this is the act of swiping the door. As we swipe the card lock and it unlocks, we get a peak here about 0.3 amperes. And it's a very short duration. This is a long, so each of these, it's thousands of milliseconds. So this is 2 seconds from here to here and from here to here. So it's a long time scale. So in this short burst of time here, we determine the energy, but then we saw that later, after you swipe the door, the lock went through another reset every time. It did a double reset every time we'd unlock the door. So you do a swipe, it would pull it back, and it would remain unlocked for about, it looks like about 5 seconds almost. And then it would relock. So this part here was the relocking energy. So we don't just unlock, but actually we spend more energy relocking. And you can hear this when you go in and out. So this is the entire energy for one sequence. You know, this would be the current, electrical current profile. So this would be the, for one sequence of entering the room. So now I'm not showing, let me just take a quick look at my next slide to see. Okay. I'm not showing here, I'm sorry. We zoomed in on it because we had a lot of data to numerically integrate this with the voltage from the battery to determine energy. So we just took the product, it was about 9 volts, and we took the product, and this entire sequence takes about 0.8 joules of energy from the battery pack. So remember, we were looking back here, we said that humans are used to putting about 3.9 joules into opening a door. We're saying we need about 0.8 joules for the unlock process. So it was encouraging to see this because now we're in that, we're above break even. Now it's a matter of how do we capture that? Yes, it's going to be an additional burden on top of that 3.9, but it's not going to be a doubling of the energy, or, it's just going to be a small incremental increase burden on the user. Okay, so we were looking at, all right. Okay, somebody's ringtone, that's good. So we were looking at electrically generating, right out of the bat, starting with an electrical generator that would mount directly to the door, nothing in between, no other steps. So we didn't want to design a generator, so we were looking at using a DC motor that we could turn its shaft a small DC motor that we could turn its shaft and use it as a generator. So those are familiar with DC motors. I mean, looks pretty simple, but this is actually a very good model for a permanent magnet DC motor. Now, these motors we're talking about, I think there's some pictures later. They're on the order of probably 1.5 inches in diameter, about 30 millimeters diameter, and length about, I don't know, a couple inches. Okay, so they're not large motors. That's about the size we were looking at. So now we were looking at finding a suitable DC motor that was available commercially that could be used as a generator in our application. So these were the parameters we were looking for. All right, we defined it. So these were the things that we then look for in vendor catalogs to try to find an appropriate motor. So this was five of them here. And we were looking at, number one, we didn't have we were running these at pretty low speed. So we were going to need one that had a built-in gearbox on it. A gear reduction would be nice. So we didn't have to have that externally. So pretty much all of these had some gear reduction between the actual motor and the shaft, which is what we needed. So this was a comparison matching up the parameters that we had identified from the model with manufacturer's specifications that they provided. So in some cases, these were not all provided by the manufacturer. We're talking, we had some money. We were able to determine the parameters if they were not provided by the manufacturer. So this was looking at a few of these. I guess that's all I wanted to really mention there. So this was a CAD model drawn in SolidWorks by our lab technician. So what we're coming up with here was, let me get my drawing tool here. So here was the actual motor, this part down in here, and here's the shaft coming up out of the gearbox. And the thing we needed was to adapt that to the door. And we came up with this bracket that fits on here. Now this is made out of steel, and it was made out of steel because the weakest part would be this little piece here. And this little piece is actually what would have to fit in between the door and the frame when the door was shut. All right. So you can picture maybe the door would actually be in here. And then the idea was that we would clamp this, and we'll see better. Oh, here's a better picture actually. So here we're looking down on it. So here we can see the door, and then the door frame would be over here. And this would fit in such that the shaft was exactly in line with the hinge pin. Right. And then as the door would swing, so in this case, this is actually showing the door open. This is the open, because here's the door frame. So when the door was shut, it would swing over to here. So we would then couple directly the motion of the door directly to the pin, because this is the one thing we did have to modify. We had to put a set screw in. We had to drill a hole and put a set screw in so that we could fix the shaft onto the moving part of the hinge. That was the only modification made to the door, was that in the hinge. One hole with a tapped hole to put the set screw. Now, the nice thing about this is we could capture energy in both directions. We could capture energy by the door opening and by the door closing, because it's up against it on two sides here. So we could get both directions. We could capture them. It would turn the motor in opposite directions, but we would rectify that in the electronics to capture it in both directions. Those familiar with power electronics, we used a boost converter. So this was the output of this was our little motor right here, serving as a generator. This was the full bridge rectifier that allowed us to run the motor in both directions and still capture the energy. Yes, we lost a little more energy by doing this, but in the rectification, but we got more than that back by being able to capture in both directions. So that was not much of a trade-off. Then this comprises a boost converter, a switching boost converter. So we would store energy in this inductor and then dump it. This would be right to the same as the battery, but we just had a capacitor there, a supercapacitor. That's what they really call them, right? Supercapacitor or ultra capacitor. 2.5 farads was what we tested with. That's a fairly large capacitance. Now, we were talking a little bit before I started also about microcode. We were running this whole switching arrangement. We were running it from a microcontroller, running at 10 kilohertz to provide the switching. But all of this then was powered from this. So we were not using any external power at all to capture. We used all energy we captured. We didn't have any external drivers. This was our prototype breadboard setup. This is showing our supercapacitor bank over here. And the nice thing now, I mean, in the last few years, supercapacitors have become even more super. They're improved. They leak less energy over time, which was nice. Balancing them is a bit of a trick. These are all in series, so it becomes a little bit of literally a balancing act. And that's what we're showing. These are balancing resistors on here that would keep all four of the capacitors at about the same charge, because they're very sensitive to over voltage charge. So we needed to keep all of them at the same voltage as we charge them. This is also a downside because this is a loss of energy. It can be a long time between door openings. So we were very sensitive to leakage and self-discharge. We had to really be careful with that. We did not, that's kind of still work has to be done there, because these would self-discharge, in a few days. So that's a bit of a downside on that. But so then this was our power electronics, and off to the side over in here, not shown, I don't know why I didn't show it, is our microcontroller that was actually driving this was our switch and our storage inductor. So coming in here, this was the wires coming from the DC generator right there. So that's what we used to try things out. So we built a prototype and mounted it to the door. This was mounted on my colleague's door. In fact, it's his office door. He retired, but his door still has the one little hole in it. We took the generator off of his door, but there's still one little hole there on his door. So we can see the door is shut in this picture. So we're up against it here. It's exactly in line with the pin. And then this section of the hinge is the part that turns with the door. And then this section is stationary to the door frame. So the wires came out, and we dressed them up here, and it came back over here to our electronics, was off board. In a final application, this would be mounted somewhere on the door. The electronics would be on the door, because you'd have to get the electronics or the power across and over to the lock on the inside of the door. We didn't worry about that, but we did want to keep everything neat on the door. And you can see the size of the motor. I mean, it's not an imposing design. We're pretty happy with that design. All right, so this was a typical opening. This is what and this is the output voltage of our generator. This was without the electronics connected. This was just the generator. So this is 2 volts for each of these divisions. All right. So we're looking at about a 10 volt peak. And then this is a half a second. Each of these is a half a second. So this was, like we saw before, it was about a 2-second opening. And actually looking at this, the voltage is directly proportional to the speed of the door, which is a bit of a downside, but looking at this, we can actually see the user's speed profile of opening door. You can see, you really start pushing the door and quickly get it going, and then let it slow down so it doesn't. I don't know if we just let it go or if we actually still had our hand on it. I'm not sure. I don't see any indication that it banged into the doorstop. So I'm not sure what our actual profile was, our actual mechanism was there. Then we took that and connected it to our actual boost circuit and supercapacitor energy storage. And that's what this is showing. So you can see now that we've connected it, we're loading it down. So we're no longer getting that 10 volt peak, we get about a 6 volt peak. And then this is the current, but this being a boost converter and it's running at 10 kilohertz. So this is actually, a 10 kilohertz rectangle wave there. And on this scale, it just looks like a blur, a blob. But notice this is 100 milliamps per division. So we were getting, peaks up to 400 milliamp. This was on the input side of our boost converter. So this amounted to a sizable amount of energy because we could take all of this and multiply it by this and integrate it to get the energy that was coming out of our converter. Okay, so what we did was to make a measure of the energy, rather than looking at that 10 kilohertz waveform and trying to do numerical integration on it, our supercapacitor on the output was already effectively integrating that current. So if we just measured the voltage on the capacitor before the door opening and after the door opening, that was an integral, and that was the change in energy. So what we found was if we had the system hooked up and we did a card swipe from our 2.5 farad capacitor bank, we would see the voltage start about 9 volts and it would drop only about 35 millivolts. It would go down by about 35 millivolts. But then as we opened the door and closed the door, we found that our capacitor voltage would increase by 50 millivolts. And what I'm showing here, that was 35% duty ratio. So the rectangular waveform was a 35% duty ratio. We had to experiment with that because the input voltage and out ratios were kind of strange depending on how fast the door opened. So we kind of arrived at a empirical value of about 35% duty ratio, gave us the maximum increase in capacitor voltage. So we can see that we have more than replaced the energy needed to open the door by one cycle of opening and closing. So that was what we did there. Then we were looking at, in the laboratory, we were looking at burden on the user, because when we had it on the door, you really couldn't feel it. It was there. You could hear it kind of buzz as it turned, but you didn't notice it, which was very encouraging because we didn't want the users to have a large burden on them. So we wanted to try to figure out, to get a measure for how much burden there actually was. So we set it up in the lab and just put a wooden stick on it and turned it. And we could measure the force on that stick. And we came up, it was about 1 foot-pound to get that same speed. Okay, so that's what our generator required, was about 1 foot-pound of torque to get a 7.5 RPM. And out at the handle, that amounted to about 0.4 pound force on the door that the user had to push, 0.4 pounds. So that works out to be only about a 13% increase burden on the user over an unloaded door. So we were very happy with that, getting more energy than we needed and a very, very small burden on the user. So we demonstrated the system. We get more energy harvested per cycle than energy used. We did not damage the door in a very large way. We had one little hole with a set screw. And we were able to do this with about a 13% burden on the user. So we feel like we achieved a good amount here. Now the downside, I mentioned about the self-discharge, and that is a problem that is almost fixing itself as the technology for supercapacitors has improved in the 6 years since we did this work. So that's a good thing. This one, this can be built into our microcode. But we have to be, like I mentioned earlier, the supercapacitors are very sensitive to overvoltage and they can be damaged. So there are commercially available electronics. ALD is a company, advanced, actually it's called Advanced Logic Devices, but they have really gotten, in the last 15 years, they've gotten more into non-digital devices. And they make a lot of integrated circuits for balancing of supercapacitors. So I would probably go with something like that rather than try to come up with my own. This is where I mentioned about we had to empirically come up with the proper duty ratio. And different users might open the door faster or slower. So I think we need sort of an adaptive method of adjusting that duty ratio for the user to always have an optimal amount of energy being stored. And then this is where I have a student working with me now. And we're looking at, actually a student worked on last year, we looked at a little about this, looking at to kind of get away from having to have the user, I don't want to say this, instead of being so dependent on the user's method of opening the door, mainly how fast do they open the door? Because remember, this DC generator is, its output voltage depends on speed. So if you have someone that opens the door very slowly, you'd need a different setup to get the same energy out. So what we were looking at before Tom retired, and now I'm picking it up again, is are there ways to have an intermediate energy storage that would be independent of the speed of opening the door and maybe only depend on how far the door is opening? So we were looking at kind of old school methods. If we were looking at like when you wind an old clock or a mechanical toy, key wound toy, you wind it, you put the energy on a mainspring, that's what it's called. And then it's just about how far you turn it. So we're looking at putting it on a mainspring. In fact, the student that worked on it last year with me was looking at using actually a mousetrap spring to store the energy. Yeah. Okay. So that way we would store the energy on the spring.
O sea, en vez de gastar ahorita.
Somebody's got their mic on there.
Lo primero que tienes que hacer es preguntarle a Alberto.
Store the energy on the spring, and then when it got enough energy on the spring, maybe to a certain tension, we would then release it and couple it to the DC generator to generate the same amount of energy all the time. That only relied on how far the door was open, not how fast. And then going back even to older school, very old school, we were looking at, instead of a spring, what if we had a small, either a reciprocating or a circular pump that as the door was opened, you would raise a fluid to a reservoir on the door, and then again, store that until a certain amount was reached, and then release that energy, and it would flow through some sort of a generator again. Again, it would be a fixed packet of energy that would be each time it reached that level. So the student working with me right now is looking at, and we're looking at getting quite a bit of energy stored each time. Now remember, we still have to then do the conversion back to electrical, but this would allow us to get over some of the other obstacles as far as the speed of the door. I'd still like to, I'm an electrical engineer, so I always think of solving the problems electrically. But so that's why we're looking at some old school methods, and there might be some merit in some of these old school methods to store the energy non-electrically. And then eventually, it has to be electrical eventually to power the lock, but having as an intermediate stage, of course, we're going to have the losses associated with that. So we're going to have to, store even more energy. But so that's where our work is going right now. We're having some fun with that right now. I don't think Ethan is here in my group. I don't see him on the list. Ethan Kuhn, he's a third-year mechanical engineering student. So he's working with me right now on this. So we hope to report on some of that at a local research conference in April. So but that's where I am. So that was what I wanted to share with you. Gladly answer questions and comments.
Thank you, Dale.
Sure.
Thank you. Are there any questions?
Yeah, go ahead. Sure. I see a hand up. Go ahead.
Jorge.
Yes. Okay.
There you go.
Well, very nice. Very nice. Well, I am a logician, not an electrical engineer, but it seems to me that at the level you're working, which is the micro level, you are very worried about the optimal use of energy. That's the key of your activity, of your project. But I was thinking that maybe the reverse logic gates, I don't know if you're familiar with that, the reverse logic gates could be helpful to your work, because that's used with the problem of the high performance computing spends too much heat. The problem with very large scale integration is the heat with the concentration of circuits.
Yep.
And then the Toffoli gates and some other, there are several that are working with gates that they discovered that in some logic, if the logic is reversible, then the entropy is not lost. You see, there is no loss of entropy. There's no generation of entropy. Okay. And that it seems to me that kind of devices that, as a matter of fact, has been used in the working of quantum computing now. That kind of devices can be very helpful to the purpose of your working, you know, which is the optimization of energy at the micro or nano level. You know, it's a kind of micro energy is where you're working, and that's very important. I believe that's very important now in the time of nanotechnology. Yeah. That kind of things can be very useful. As a matter of fact, the way I discovered this is trying to investigate or to learn, really, because I have to learn about quantum computing. Okay. And one of the key factors in that is the reduction of entropy, the entropy generation on the high levels of integration.
Okay, well, thank you. I'm open to a lot of things, and like I said, I'm looking at very old school things. You know, looking at water, using water to store energy, sand, you know, things like that. So, but okay, well, thank you very much.
I will put the name of Toffoli. Toffoli, he's an Italian. He's famous because he was here. There's more circuits done, but he is the most famous. I will put it on the on the
thank
chat.
You. So,
Alfredo.
Got out of that. Yep, sure, go ahead. I think he's muted. Oh, there you go.
Dr. Dale, thank you and congratulations for the interesting presentation.
Thank you.
And to us a lot of possibility of solving our problems. We have serious situation of lack of electricity here in our country. No, sometimes we're unable to work online or just charge our mobile phone equipment. No? I have a couple of questions I would like to ask. What will be missing to turn this initiative in a commercial product? Are you nearby? Or the second question is, if instead a door, for example, a hand mill could be used, a hand mill, those ones they use for green corn, and then used to create energy and to charge a mobile device or just to charge the battery of the laptop, for instance, no? And another question is, how could this invention be applied in a remote region, or for instance, on a farm or in an indigenous community, for example, for telemedicine purposes, that the patient could explain to the doctor about the symptoms he feels, and the doctor just gives some instruction, the simple communication. Three small questions.
Yeah, okay, great. Well, the first question, I think you asked about commercializing this, and that's where, that would involve working with the lock manufacturer. I don't know how open they would be to, because we're going to have to connect from the outside world into their lock. Since it is a lock, it involves security. So that's why we did everything on the inside of the door. So it's on the secure side of the door. But for that manufacturer, I haven't had any talks with the manufacturer, but that would, we'd have to see, it has to become a change of philosophy at how they power, because they do actually have an option in our other building on campus. The locks are actually powered through wires that come through the door frame and over into the lock. They don't have batteries at all. But I think we're going to see, as we see more of Internet of Things, which I hated that term when it first happened, but as we become, as processing is everywhere, like this lock, it's web enabled. That's why it needs a lot of the energy. So if we can have the energy generated at the source where it's needed through, like I said, things that can be scavenged, whether it's solar or mechanical motion or, that's vibrations. Vibrations is another big area. Now, there's not a lot of vibrations on this door, but that's the kind of, progress that we're seeing. Now, I think I'm not your second question, but your third question about applying this kind of thing to remote locations. That's where it becomes kind of a change in the way we think about energy and how it's used. Like right here, we're talking about generating the energy at the door where we use the energy. So I don't know if anything I'm doing directly can be applied to a rural setting, other than the idea of, instead of having a central location of the power being generated, if it's more distributed, closer to where it's used, that can, tend to reduce some of the burden, in that if one goes down, you don't lose power for everything. It's at the source where you use it. I'm just thinking, like, if farmers had electric fence, right, around their property to contain their livestock. And there is a lot of this where they use solar to generate that, because that's with electric fences, it's a pulsed application. So it's not a lot of energy needed all the time. So that can be harvested and stored locally. And, you don't need to have a grid, converter and everything to drive your electric fence. Folks we worked with in Australia on a different project were using solar energy to power cell phone towers in the outback. And previously they had diesel generators there to power it. But now they're actually storing the energy in batteries from sunshine, and they have the diesel generators just as a backup. So they used to have the batteries as a backup for the generator. Now the generator is a backup for the batteries, because the battery technology allows them to store more energy right where they're using it. And they have no wires going there. There's no grid tie at all to that. So I think it's almost like we're going backwards. You used to have a windmill on your farm to pump your water, and now they got electricity, and then they didn't need the windmill. I think you kind of go back to the idea of maybe having a windmill that generates electricity to generate your pump to turn, so I think for a farm level scale or farm scale, I think you're looking at larger things unless you're getting into livestock that are turning treadmills and things like that. And I don't know if you want to go that direction, but water is a good one too. If there's any source of water on the property that they can, you know, turn a generator, you can get a lot of energy, surprisingly, from very small generators. That's just my thoughts on it. I don't, you know, it's just the philosophy of using energy, generate it where you use it. It's kind of going back in time, but that's what the Internet of Things is making us do. In factories, they use vibration from machines to generate electricity to power the equipment that's monitoring the machine. And that's a very common thing now because it's quick. There's no wires to install it. It just maybe has a magnet that sticks on to a particular motor or a pump that vibrates all the time, just a little bit, enough to generate energy for infrequent transmission, you know, wireless transmission of, you know, temperature of the machine or vibration of the machine or just even the vibration of the machine to determine machine health. And they don't have to run any wires to the machine. So they're generating energy where they need it. So that's the connections I see. I didn't remember your second question, Alfred. So
the second question was related. The idea was if instead the way you are doing it with the door, use a hand mill that can
right, okay, right,
and then use energy to charge a mobile device or charge the laptop battery.
And yeah, I mean, you can buy those. Those are available. You know, the hazard radios in the United States. You can buy the radios to receive emergency broadcasts and just listen to radio. And they have built-in USB chargers, and it's got a hand crank on the end. And this is really old technology. I mean, in World War II, they used radios that they cranked it and then talked. But it's tried and true. And again, that's at the source. You can buy flashlights like that for camping that have now a built-in USB plug on it. So while you're sitting around the campfire, you can turn the crank, or they have them as you can kind of a repetitive squeezing motion. You know, you can use trade-off hands. I have one in my office, actually, just for students to play with. It's from Eddie Bauer company, and we can squeeze it and it charges. Actually has a supercapacitor inside that you charge, and then it runs an LED flashlight for several minutes. So yeah, I'm a fan of those. Yeah, they never go dead. Just pump it up and it works. Yeah.
Hey, I have a question for you.
Okay.
Well, hotels use the same, use electronic locks. And I presume they have the same problem that they run out of, the batteries run out of energy.
Unless they're wired. Like I said, our new ones in the Lursum building are wired, but they're trying to get away from the wired ones because, the wired ones have their own, maintenance issues, and initial cost is higher to install them all, to run all that wiring. So I'm sorry, go ahead. So yeah, hotel. Yeah, I mean.
No, I was going to ask you if they have the same problem, or, I mean, I can see how you're approaching this because, you have a door, you have motion, you have energy there, and you have boundary conditions as, we don't want to change the door. We want to keep it the way it is. We just want to hook up to the hinge, and so, it's a very nice solution. So
yeah, one application that I've seen on an even smaller level was on, I believe, the Boeing Dreamliner aircraft. For the passengers, the overhead buttons that you push to call an attendant, or that button has no wires going to it. When you push it and release it, it actually has a magneto that generates enough energy to send a wireless signal to somewhere as an antenna in the cabin, and indicates that it was like an RFID. It says that button was pressed, and it turns on a light for the attendant to know who pressed it. There's no wires going to it. It's just press the button and release it, and it generates enough energy to tell where it is. So yeah, that's really right at the point source. But you can figure if every seat needed wires going to it, for that button, that's weight, that's wiring. So those are kind of neat. So
interesting.
But the hotel door, yeah, I mean, they would be in the same boat as our building. It's the same idea.
Well, there you have a customer though.
If they are using the, if it is battery operated, yeah. I'm an academic right now though, so we're not taking it to the next level yet. We got to make it work a little better, I think, to take it to the next level. But just giving this talk, I'm more excited about it again though. So.
But I remember when I was there, I mean, we complained so much about the locks because the battery ran out. And it was a mess. I mean, we would have, at any given time, we would have at least one faculty member without a way to get into his or her office.
And Janelle has sent a message. She says there's still a mess. Yes, thanks, Janelle, for supporting my case here. Yep, that's right.
Right. I think we are. We're right on time.
Okay.
Alfred. I think
there's one message in Spanish. I see gracias at the beginning, so I think it's a thank you for
that's right.
Giving the talk. I'm not sure.
Thank you for the invitation.
I took French in high school.
Presentation, Dr. Leitweiler.
Okay. Well, thank you.
Es un ameno presentador. So you make it light and easy. So. But I was I didn't say anything about this, but I was Dale's supervisor for a while, and then I should ask permission from him to say this, but I'm sure he would agree that his most frequent comment from the students was that he is very funny. He uses humor to drive concepts through. So.
Yeah, I was careful tonight because I don't know if some of it might be lost in a
translation.
Yeah, a little. Yeah. So
the other thing that I forgot to say about Dale, or we forgot to say, is that Dale is a licensed non-commercial pilot.
Yeah.
So he likes risk.
It's calculated risk and minimized risk, but yeah, that's what we say we're doing.
He invited me to take a ride with him on his plane, and I said, yeah, we'll talk about it later.
I'll take him up on it.
Okay.
There you go, Francisco.
Well, you live locally. Well, you live in Wayne, I guess, or area.
Yeah, I just moved to Wayne. So I used to live in Jersey, and I just moved to Wayne. But all my friends live a bunch of my friends live in the Reading area. So quite a bit.
I fly out of the Reading airport. I'm in the Reading Aero Club, so we. I won't fly as much as I like to, but I do enjoy it.
I think Alfred has a question.
Oh, okay.
I would like to add something else, Dave. In our country, in this moment, the companies that take care of the cell phone companies, they have a serious problem in the radio base. They have a vandalism situation. The people take the batteries, the inverters, the cables, and they are thinking in photovoltaic cells, those solar panels, but also aluminum is attractive for vandalism. What kind of options do you think are viable using the project you are handling with, this kind of idea that you are by sure that you have how to provide energy for a radio base for those cell companies?
For the antennas, for the
antennas,
cell phone antennas.
Radio
for the towers.
Yeah.
The towers,
yeah. Well, that was where that company we worked with in Australia, who was then actually was a battery company, and then they were purchased by a local battery company here in the United States. And that was, their idea was to be able to have high density battery storage to store, because in the outback of Australia, there was plentiful sunshine. So that was kind of unique to that, is that they could store a lot of energy to carry them through the night just from battery storage. And that's high. We're talking about quite a bit of high power there, you know, hundreds of watts continuous, you know, to power everybody's got a cell phone, even in the outback. So they have to, so I don't know if I'm answering the question, but yeah, that's kind of as not everything scales. And when we go to that level, you know, obviously we're still doing trying to be more efficient, as you know, that's always going to be the
I think what Alfredo is saying is that the cell towers are vandalized, burglarized, dismantled. You know, people take away. So okay. I think we're talking about some design to electrocute vandals to give them a shock, not electrocute.
See, you get to that point is, you know, you don't want to kill somebody for vandalizing a cell phone tower, you know. So I think, I don't want to sound like a socialist, but I think you have to figure out why they're vandalizing it in the first place. Maybe if they had a job, they wouldn't do that. I mean, I don't know. So other than having, you know, better fencing and better security patrol, I mean.
But this is what Alfred is saying, that even the aluminum, which or the metal that they use for the fencing, they take it away and sell it.
Attractive.
I guess you'd have to have it suspended from a balloon or something so that they could get to it. I mean, yeah, that's where I think Elon Musk is. They're trying to get to that, you know, low Earth orbit satellite system for internet. Then they can't vandalize it. You know, and those are, you know, those are pretty small satellites, like the size of a refrigerator. Or smaller. So yeah, boy, vandalism, that's like a age-old, they used to rob the pyramids, you know, so what are you gonna do? I mean, I don't know.
I think that's a problem of culture and of hunger.
Sure. Yeah.
Poverty. Yeah.
Yes, it is. But probably the folks that were vandalizing the tower had a cell phone. I'm just guessing, but maybe they didn't.
They do.
You can bet it.
But then they don't have any service. See, if you vandalize your tower, and then you lose your service.
Yeah. That in Venezuela, that was not like that 40 years ago. No, it was not like that. That came when we have a kind of system, political system that have poverty. You know, everybody is poverty. Is poor. I am poor now. I am paying the whole income of this year from the university was the $700 in the year. That was my income as a full professor.
You need to come to the United States. It's a little bit more in the United States. Is Janelle still on there? Yeah, Janelle's still there. Okay, yeah.
All right. Alfred, are we out of time or?
Well, I don't know if somebody else wants to ask.
Is there a meal with this? I thought there was going to be a meal.
No,
that's a joke. Meal. That's a joke. Yeah.
We're making a steak with your hinge powered kitchen.
Okay. I mean, if you have this sometime, I'd come to Venezuela to, you know, if they get a meal out of this and talk to you, you know. So.
Yeah. Well.
Okay. Well, if there was no other question, like, you know, thank you folks for inviting me. I really enjoyed doing this.
Thank you so much.
It was good to have some people on this side and some folks in Venezuela, and nice meeting you all.
That was fun.
Yeah.
Thanks, Dale.
Thanks, Janelle.
Oh, Janelle showed up.
Yeah, huh? She's been there. Yeah,
she talks.
Yeah. I've been lurking.
Left. Yep.
All right.
Thanks,
see you later. Thank you.
Well, thank you, Dale.
Hey, Alfred.
It's been great. Thank you so much.
Bye,
bye, everyone.
Bye.